Continued. Now let's see how we can prove angle 1 equals angle 2. So as can be seen that we have proved angle 3 is equal to angle 4, which is already proved. Now using this, let's see, angle 3 can be written as 180 minus angle 1 because the whole of 180 degrees minus angle 1 gives me angle 3. Therefore, angle 3 can be written as 180 minus angle 1, and similarly my angle 4 can be written as 180 minus angle 2. Therefore, this comes out to be 180 minus angle 2. The two 180 degrees being equal can be cancelled, and therefore minus angle 1 equals minus angle 2, and finally I get this to be angle 1 equals angle 2. Is how I conclude angle 3 equals angle 4 and angle 1 equals angle 2. Therefore, vertically opposite angles are always equal. Is how we conclude the property. Vertically opposite angles are always equal. It's universally true, as proved mathematically out here. Property and its theorem. Now that we have discussed the various properties, theorems and axioms related to linear pair and vertical pair, vertically opposite angles, let's see some applications of the properties in real life. Applications of linear pair and vertically opposite angles. Applications of linear pair and vertically opposite angles is the topic of the session. So let's see some applications related to the theorems and axioms as learnt in the previous sessions related to linear pair, adjacent pair and vertically opposite angles. Imagine I have a problem which says ABC is a triangle. Say for example, I have a line L which intersects another line L2, and there is a ray passing by out here. Now here I have this to be (40 degrees), and then this is given to be 30 degrees. So here I have a problem which says this angle is 40 degrees and this is 30 degrees, and I need to find this angle, and also I need to find this angle and this angle. So here is a question which relates to linear pair and vertically opposite angle properties. So let's see how we can find each of these angles using the condition of 30 degrees and 40 degrees. So let's see how we can find this. As we can clearly see that this is equal to this, as they are vertically opposite angles. If I take the line L1 and L2 irrespective of the ray, I clearly see that this being 40 degrees must also be equal to this angle, which is 40 degrees. Therefore, this angle must be 40 degrees. Because since they are vertically opposite angles, and vertically opposite angles are always equal in the pair of lines intersecting. So this equals this being 40. Now let's come to this angle. Now we know that L2 is a straight line, and therefore in a straight line, this angle plus this angle plus this angle, each of the angles must be equal to 180. Sum of each of the angles must be equal to 180. So angle this plus angle this plus angle this must be equal to 180. As we can see, if I take the line L2, which is a straight line, I see that this is the angle made by L1, which is 40 degrees, and this is the angle made by the ray, which is 30. But this is 30 degrees, and the remaining angle is what we need to find. So this being a straight line, the sum of each angle, sum of all three angles must be 180. Therefore, this angle will be 180 minus 30 plus 40, because the whole of 180 minus this gives me the required angle, which on further simplification gives 180 minus 30 plus 40, which is 70, where 70 when subtracted from 180 is 110. Therefore, if I take this as x, this as y, and this is z, my angle y would be equal to this. Angle y equals 110 degrees. Now that I have found each of the angles, now the question comes on how to find z. So let's see how we can find angle z, continued from angle x and angle y. To find angle z, now clearly, as I see, the sum of all the angles taken here must be equal to the circle angle, that is 360, because this angle x plus 30 degrees plus this plus this plus this forms one full circle, in which angle in one full circle is 360 degrees. Therefore, I get the circle property coming into existence here. That is, from the diagram, this, I clearly see that 40 degrees plus 30 degrees plus 110 degrees plus 40 degrees plus z must be equal to 360 degrees. Is how we get from the circle property by circle angle, or since this is a circle angle, it must be equal to 360 degrees. When I add this, 40 plus 30 is 70, and 70 plus 40 is 110, which is 220, plus z equals 360 degrees, which on further simplification gives, that implies z is 360 minus 220, that implies my z is 140 out here. So my angle z is equal to to 140 degrees. Using the circle angle, I can find each of the angles, angle X, angle Y and angle Z, with their own respective approach. Given the angles, we can find the adjacent or the vertically opposite angles using the properties as learnt in the previous session. Real life applications of linear paired and vertically opposite angles. Transversal. The next topic in the session is about discussion of transversal. What is transversal? Let's see the definition and its property in more brief in the session. Transversal. What is transversal? As we see, imagine I have two lines L1 and a line L2. Any line which intersects L1 and L2 at two distinct points is called a transversal. Say for example, I take a line which cuts the line L1 at P and the line L2 at Q, then this line is called the transversal. Transversal is a line which cuts two or more than two lines at two distinct points P and Q. This is the transversal for these two lines. Is how we understand the transversal. Imagine I have L1, L2, L3, L4, L5 and L6. There are 6 lines out here, and then there's a line which cuts this at A1, A2 and cuts L3 at A3 and cuts L4 at A4, L5 at A5. Then this line which cuts each of the lines L1, L2, L3, etc. till L6 at different 6 distinct points A1, A2, A3, A4, A5 and A6 also is called a transversal. A transversal does not have a restriction on 2 lines, but there can be any number of lines through which the line must cut at distinct points. So this is also an example of a transversal, as how we understand the transversal property of the condition. Is how we understand this. Imagine I have a line L1 and line L2, and here I have a line which cuts L1 at P but does not cut the other line. Therefore, this cannot be a transversal for L1 and L2. Is not a transversal for L1 and L2. Is how we understand the transversal property in mathematical understanding. Transversal is a line which cuts more than two lines at 2 distinct points or at all distinct points. Is how we understand transversal in geometry. Parallel lines. As we have discussed about parallel lines in many instances while coming across in theorems, axioms, solving problems, let's see in brief about what are parallel lines and what are the mathematical properties related with parallel lines. Parallel lines and its discussion. What are parallel lines? Imagine we have a railway track in which the 2 rails are exactly at equal distances. There is no possibility that the 2 rails meet at the railway track. So the railway track can be taken as an example of or parallel lines which are separated by this grids out here. The two rails, this is rail 1 and this is rail 2, and the two rails never meet, but they go on and on and on, but they never try to meet, is how we understand the two parallel lines. So mathematically, when I connect these two rails with the railway track, I clearly understand that this is an example of lines which are parallel. Since these two never meet, they are parallel. So mathematically, I define the parallel lines to be those lines which never meet. They always go on and on till infinity, but they never meet, is how we understand the parallel lines. Parallel lines and its properties to be continued further. Now let's take two parallel lines to understand the further properties related. Imagine I have two parallel lines, L1 and L2. So these two lines are parallel because they go on and on, but they never meet. And interestingly, there will be equal distance at every pair taken on the two lines. They are at equal distances everywhere. And let me say there's a transversal which cuts the lines L1 and L2 at these two distinct points, these 2 points of intersections. Now, as we can see that the transversal, when it cuts both L1 and L2, makes 4 angles with L1, 1, 2, 3, 4. This transversal, when it cuts line L1, makes 4 angles, 1, 2, 3, 4 with this, and makes the other 4 angles with the line L2 out here. So totally there are 8 angles formed by the two lines which the transversal cuts with. Is how we connect the properties. A transversal cutting the lines L1 and L2 which are parallel. L1, L2 are parallel as they never meet. Because they never meet, they are parallel. And let's see how are the properties related with the parallel lines with the transversal. So let's see the interior angles in the parallel lines. To start with, the first property related with interior angles. So parallel lines connected with interior angles. Is what we are going to discuss in the session. So let me take two parallel lines. L1 and L2. And let me have a transversal which cuts the lines L1 and L2, thus making 4 angles here. 1, 2, 3, 4, 5, 6, 7, 8. Now, out of these 8 angles, we call the interior angles as those angles which are in the interior region of the parallel lines. So clearly I can see that this and this are in the interior region of the parallel lines, where 1, 2, 7 and 8 are said to be outside, that is in the exterior region. So interior angles are the angles in the interior region. So let's see what are the angles in the interior region. Angle 3, angle 4, angle 5, angle 6 are said to be the angles in the interior region, and therefore these angles which are in the interior region of the parallel lines are said to be interior angles. Interior angles in the parallel lines is angle 3, angle 4, angle 5 and angle 6. Now let's see the exterior angles. Now that we have discussed about interior angles being the angles in the interior region of the parallel lines, exterior angles is the pair of angles which are in the exterior region of the parallel lines. It's very simple, as similar as the interior angles. So let's see exterior angles in the pair of parallel lines through the transversal. Exterior angles. Let me take the pair of parallel lines L1 and L2 with the transversal cutting the lines L1 and L2. And making 8 different angles with L1 and L2. Now clearly when we see in this, we see that angle 1, angle 2 are the exterior of a line L1, and angle 8 and angle 7 are in the exterior region of the line L2, wherein this is in the interior region of the parallel lines. So this 2 and this 2 being on the exterior region are called the exterior angles. To be followed with exterior angles are defined to be angles in the exterior region of the parallel lines. So here the exterior angles are angle 1, angle 2, angle 7 and angle 8. So here these 4 angles being on the exterior region are called exterior angles. Exterior angles in the pair of parallel lines. Angle 1, angle 2, angle 7 and angle 8. Now that we have discussed about interior and exterior angles in the pair of parallel lines, now comes the corresponding angles. So let's see what are corresponding angles in the pair of parallel lines. Corresponding angles in the pair. So let's take one pair of parallel lines L1 and L2. Let there be a transversal which cuts the 2 lines. Now for this transversal, as we already discussed about 8 angles which are formed with L1 and L2, we have 1, 2, 3 and 4, 5, 6, 7 and 8. Then the corresponding angles are said to be the angles which are correspondingly above lines L1 and L2. So if I have this angle 1, my corresponding angle with 1 is said to be angle 5, and corresponding to angle 2 we call 6 to be corresponding. Corresponding to 3, that is, an angle which is below L1 is corresponding to the angle which is exactly below L2. So this is corresponding to this. An angle which is below L1, which is 4, corresponds to an angle which is below L1, corresponding exactly in the same region. So these are called corresponding angles in the pair of parallel lines. Corresponding angles are the angles which correspond to the same region. So angles which correspond to the same region are corresponding angles. In this case, angle 1. And interestingly, in parallel lines, the corresponding angles are equal only when the lines L1 and L2 are parallel. Therefore, angle 1 equals angle 5, which are corresponding, and angle 2, which is out here, is equal to angle 6. And angle 4, which corresponds to angle 8, are equal, and angle 3, which corresponds to angle 7, are said to be corresponding angles and are always equal. Therefore, I have a property which says L1 parallel to L2 is the symbol for parallelity. So when line L1 is parallel to L2, implies corresponding angles are equal always. Or always equal. So L1 parallel to L2 implies corresponding angles are always equal when lines L1 and L2 are parallel. Corresponding angles connected. Now that we have discussed about corresponding angles and all the corresponding pairs being equal in parallel lines L1 and L2, next comes the property of alternate angles. So let's see what are alternate angles in the parallel lines. Alternate angles. Imagine I have two parallel lines L1 and L2. Divided by a transversal. Then we know that there are 8 angles which are formed with L1 and L2, which is 1, 2, 3, 4, 5, 6, 7 and 8. Now here we call the alternate angles which are on the vertically opposite side. So they are on the vertically opposite side, and this is vertically opposite to this. No, this is vertically opposite. So we have alternate angles which are alternate to the transversal. So clearly I see that this is alternate to this and this is alternate to this. So 3 and 5 are alternate, 4 and 6 are alternate to each other. So I have alternate angles to be angles which are alternatively in the region of either side of transversal is what we define as alternate angles. So have this angle 3 and angle 5 are alternate angles, and therefore they are equal in parallel lines. The parallel line property says that alternate angles are always equal in case of two lines L1 and L2 being parallel. Therefore, angle 3 is 5, angle 4 is equal to angle 6, and these four angles are called alternate angles. And mathematically, we have the property which says L1 parallel to L2 implies alternate angles are always equal, is how we have the property which says alternate angles are always equal in case of two lines L1 parallel to L2. Alternate angles 3 and 5, 4 and 6 in the pair are equal in parallel lines. Now next is the discussion of vertically opposite angles when two lines L1 and L2 are parallel cut by the transversal. Vertically opposite angles in pair of parallel lines. Vertically opposite angles. Let's see what are vertically opposite angles. Imagine I have two parallel lines L1 and L2. Line L1 and line L2 cut by a transversal. Now we know that there are 8 angles as made by the lines with the transversal. Now vertically opposite are the one which are vertically opposite each other, as we have already discussed about vertically opposite angles. These two are opposite and these two are opposite. Therefore, in case of this vertically opposite angles are which are opposite to each other, as can be seen, one is vertically opposite to 3 and they are always equal, as proved in the previous theorem. Vertically opposite angles are always equal. So 1 equals 3 and 2 equals 4. Similarly, 5 and 7 and 6 and 8 are all the possible pairs which are equal in parallel lines. These are vertically opposite angles. Therefore, when the lines L1 and L2 are parallel, their vertically opposite angles are also universally equal. Corresponding angles, alternate angles, and vertically opposite angles are always equal in case of two lines being parallel. Interior and exterior angles connected with parallel lines. Now that we have discussed various properties connected with two parallel lines and the transversal, now comes the most important property called interior angles on the same side of transversal. Let's see how this plays a vital role. Interior angles on the same side of transversal. On the same side of transversal. So imagine I have two lines L1 and L2 which are parallel to each other. I have a transversal which makes four angles with L1 and L2. Angle 1, 2, 3, 4, 5, 6, 7 and 8. Now, when we discuss about interior angles on the same side of transversal, we have already discussed about totally there are four interior angles in this, that is angle 4, angle 3, angle 6 and angle 5, which are interior angles. Now out of this we clearly see that these two are interior angles on the same side of transversal, and these two are the interior angles on the other side of the transversal. Therefore, as seen from the diagram, angle 4 and angle 5 are said to be interior angles on the same side of transversal. Similarly, angle 3 and angle 6 are the interior angles on the other side of the transversal, of course on the same side. Also, angle 3 and angle 6 are interior angles on the same side of transversal. Is how we understand the interior angles connected with the parallel lines L1 and L2. Interior angles on the same side of transversal. Also, the interior angles on the same side of transversal are also referred with the names allied angles, or they also referred to be co-interior angles. So there are different names out here, and the interior angles on the same side of transversal are sometimes referred as allied angles or co-interior angles, or they are also referred as consecutive angles, which are the different names as given for interior angles on the same side of transversal. Consecutive interior angles is how we give different names for the interior angles on the same side of transversal, which are also called allied angles or co-interior angles or consecutive interior angles. Is how we understand the interior angles on the same side of transversal connected with the parallel lines. Now that we have discussed about interior and exterior angles, and most importantly in the previous session where interior angles on the same side of transversal or the allied angles which we have discussed, let's see the mathematical property which connects interior angles on the same side of transversal connecting with supplementary angles. Interior angles versus supplementary angles. Let's see how the interior angles are connected with the supplementary property. So let's take two parallel lines L1 and L2. Here is line L1 and here is line L2, which are parallel to each other. Now with these two lines being parallel, let's take a transversal out here. Now with this transversal, we know that there are 8 angles formed, with 4 angles formed with L1 and 4 angles formed with L2 is how we connect the 8 angles which the transversal forms with L1 and L2. Now we know that the interior angles on the same side of transversal are 4 and 5 and 3 and 6. So angle 4 and 5 and angle 3 and angle 6 are the interior angles on the same side of transversal. Now the property says that in mathematics, the pairs angle 4 plus angle 5 is always 180. This plus this is 180 and this plus this also is 180. Is how we see the properties. Interior angles on the same side of transversal are supplementary. The sum is 180. Therefore, angle 4 and angle 5 are supplementary angles. Angle 3 and angle 6 are also supplementary angles, is how we understand the pairs being supplementary angles. Interior angles on the same side of transversal are equal to 180, that is, they are supplementary angles. Now that we have discussed about various properties connected with parallel lines, now let's see the reverse process of understanding the same properties. Parallel lines connected with reverse process. So what is this reverse process? Say for example, we have discussed in the previous session that when two lines are parallel, their corresponding angles are equal. Now my question is, if the corresponding angles are equal, will the lines be parallel? So we are investigating now in the reverse process. Imagine I take two lines which are not parallel. Say I take two lines somewhere in this manner, and I just take a transversal out here. Then we know that there are 8 angles formed, 4 with L1 and 4 with L2. Now, when I say that the corresponding angles are equal, let's see if the lines are parallel. So as we know that the corresponding angles are same, that means angle 1 and angle 5, angle 2 and angle 6, angle 3 and angle 7, angle 4 and angle 8 must be same. So let's draw two lines randomly with the transversal and measure each of the angle, 1 with 5, 2 with 6, 3 with 7 and 4 with 8. So when we measure the angle 1 with the protractor, we should also equally measure the angle 5 with the protractor out here. Then let's see if the angles are equal. If the angles are not equal, then we can say that if the lines are not parallel, their corresponding angles are not equal. If the corresponding angles are equal, then let's take the case where the corresponding angles are equal. So here 1 2, 3 and 4, 5, 6, 7 and 8. So let's take the case where the corresponding angles are equal. Then the property says that if the corresponding angles are equal, then the lines which follow that angle and the transversal must be parallel. If the lines are not parallel, then we cannot have the possibility that the corresponding angles are equal. Therefore, if the corresponding angles are equal, then the lines L1 and L2 must be parallel. This is how the property comes as converse of the lines L1 and L2 are parallel, the corresponding angles are equal. If the corresponding angles are equal, the lines L1 and L2 must be parallel. This is how the reverse process of understanding corresponding angles connected with parallel lines. Now let's see the reverse process connecting the alternate angles. As we know that when two lines L1 and L2 are parallel, their alternate angles are equal. Therefore, now let's investigate if the alternate angles are equal, will the lines be parallel? Reverse process of parallel lines, reverse process connected with alternate angles. Alternate angles. The lines L1 and L2 which are not parallel divided by the transversal and having the angles out here, we know that the alternate angles are 4 and 6. If angle 4 equals angle 6 and angle 3 equals angle 5, that is, if alternate angles are equal, then the property says that with the alternate angles being equal, the lines must be parallel. There is no other possibility but the lines L1 and L2 must be parallel. If alternate angles are equal, then the lines L1 and L2 must be parallel. That is, L1 parallel to L2 is how we understand the reverse process. If the lines L1 and L2 are parallel, alternate angles are equal. But if the alternate angles are equal, then the lines L1 and L2 also must be parallel. The reverse process of understanding alternate angles connected with parallel lines. Now let's see the reverse process of connecting interior angles with the parallel lines. Parallel lines in reverse process connected with interior angles, or in this case more specifically called allied angles, on the same side of transversal being called allied angles. As we have seen in the previous properties that if x and y are allied angles in the parallel lines L1 and L2, then x and y are supplementary angles. That is, x plus y must be 180 if x and y are allied angles, because they are interior opposite angles or interior angles on the same side of transversal. Now comes the question of reverse process. If the interior angles sum up to supplementary or sum up to 180, will the lines L1 and L2 be parallel? This is the biggest question out here. So let's investigate on interior angles connected with parallelity. Let's take two lines, L1 and L2. These two are the lines L1 and L2 divided by a transversal. It makes four angles, 1, 2, 3, 4, 5, 6, 7, 8 is how I get 8 different angles. Now we know that angle 4 and 5 are interior angles on the same side of transversal. Angle 4 and angle 5 and angle 3 and angle 6 are interior angles on same side of transversal. So let's see with the property that if angle 4 and angle 5 are supplementary and angle 3 and angle 6 are supplementary, then the reverse process says that given the condition that interior angles on the same side of transversal are supplementary or the sum is 180, then L1 must be parallel to L2 is how the condition states in parallelity. So the reverse process holds for corresponding angles, alternate angles and interior angles on the same side of transversal, that is for allied angles, is how we understand the reverse process being true for all the three connected angles for the parallel lines L1 and L2.